What if I told you that while you're listening to these words right now, you're witnessing the greatest magic trick the cosmos has ever performed? The device in your hands, the air filling your lungs, even the thoughts racing through your consciousness. Every single piece of this reality materialized from absolute void, not emptiness that contained something tiny, not space waiting to be filled. Complete, total nothingness, transformed into everything you've ever known or will ever encounter. Stop for a moment and consider this staggering fact. Surrounding you at this very instant are approximately 10, followed by 80 zeros worth of fundamental particles. These microscopic building blocks flow through your bloodstream, construct your bones, create the light entering your eyes. Yet 14 billion years ago, not even one of these essential components existed anywhere in the cosmos. Zero atoms, zero molecules, zero matter of any kind. Welcome to an extraordinary exploration that will revolutionize how you perceive existence itself. Tonight, we're embarking on humanity's most ambitious quest, unraveling the ultimate mystery of how our universe conjured everything from pure nothingness. We're not discussing rearrangement or transformation of existing materials. This journey reveals the breathtaking moment when reality itself began, when the very concept of something emerged from conditions where even that word held no meaning. Before we venture into this cosmic revelation together, I invite you to share your current location and local time in the comments below. Your engagement means the world to me, so please show your support by hitting the like button and subscribing for more mind-expanding content. Trust me, what you're about to discover will change your perspective forever. Our expedition tonight transcends simple explanations of atomic behavior or particle composition. We're traveling backward through time to witness the universe's birth when it occupied less space than the tiniest punctuation mark. You'll observe matter's first breath, watch fundamental forces emerge from chaos, witness protons and neutrons assembling from pure energy, while electrons began their eternal dance that eventually became chemistry itself. Here's where this story becomes beautifully paradoxical. The formation of atoms from nothingness isn't merely ancient history locked in the past. This incredible process continues influencing reality in ways that will transform your daily experiences. When we conclude tonight's journey, that glass of water beside you will never appear ordinary again. You'll recognize that each drop contains particles forged within stellar cores, cosmic wanderers that traveled billions of years and countless distances just to become part of your evening refreshment. The adventure awaiting us spans dimensions so enormous, they challenge human imagination. Our story begins in a realm where time might not have existed, where space compressed into measurements smaller than anything our instruments can detect. We'll experience the universe's initial expansion, that explosive birth when everything familiar started spreading from conditions of infinite density and temperature that defy comprehension. This isn't fantasy masquerading as science, though it certainly sounds impossible. We're exploring cutting-edge cosmology supported by decades of observations, mathematical frameworks, and experiments pushing the limits of human understanding. We exist during a remarkable era, when researchers can actually trace cosmic history back to fractions of seconds after creation began. Scientists map the cosmic microwave background radiation creation's afterglow, still resonating through space after nearly 14 billion years of expansion. But before examining the spectacular moment when atoms first organized themselves from early universal chaos, we must grasp what we're actually investigating. What defines an atom's true nature? Most people imagine them as tiny solid spheres, like microscopic balls colliding and interacting with each other. This mental model helped early scientists develop theories, but reality proves far more mysterious and elegant than those primitive concepts suggested. Atoms consist primarily of vacant space. Picture magnifying one atom to a football stadium's size. The nucleus would appear smaller than a marble positioned at midfield, while electrons would buzz somewhere in the highest seating areas. Despite this mostly hollow structure, these particles create the solidity of everything you touch, compose every breath you draw, form every photon reaching your retinas. Electrons don't actually orbit like planets circling a star. Contrary to those familiar atomic diagrams, they inhabit probability regions, zones where they might be located if somehow measured and observed. They simultaneously exhibit particle and wave characteristics, defying our everyday understanding of how objects should behave. This quantum strangeness isn't merely abstract scientific theory, it represents reality's fundamental nature, the bizarre rules governing existence at its most basic level. Each atom's nucleus contains a dense cluster of protons and neutrons bound together by forces powerful enough to overcome electromagnetic repulsion between positively charged protons attempting to separate from each other. The strong nuclear force, as physicists term it, operates roughly 100 times more powerfully than electromagnetic force at these microscopic scales. Without this binding strength, no nucleus larger than hydrogen could maintain stability, leaving the universe far simpler and completely different. These forces, particles, and quantum mechanical behaviors that seem so foreign to our daily experience all had to emerge from absolute nothingness, not from pre-existing materials that got reorganized, not from energy already present, awaiting arrangement, from complete void without any foundation whatsoever. This concept challenges everything our minds naturally understand about cause and effect. We inhabit a world where everything originates from something else. Trees grow from seeds. Seeds develop from mature trees in endless cycles of transformation. Even in our most sophisticated laboratories, when scientists create new elements or discover unusual particles, they always begin with existing materials, converting current matter and energy into different configurations. Yet the universe appears to have created itself, emerging through cosmic mechanisms that didn't previously exist. This represents more than a philosophical puzzle or knowledge gap awaiting solutions. It's a fundamental characteristic of existence that demands we expand our comprehension of what's genuinely possible in our universe. The mathematical equations that decode this cosmic birth story possess an elegance that leaves physicists breathless. These formulas link gigantic galactic structures with subatomic particle behaviors, creating theoretical bridges spanning impossible distances. The precision of these calculations predicting elemental abundances across the cosmos remains stunning in its accuracy. Through these mathematical tools, we can essentially time travel backward through dimensions and epochs, witnessing creation's first breath. However, mathematics represents only one layer of tonight's extraordinary revelation. Beyond numbers and equations lies something truly magical. Recognizing that carbon particles forming your physical structure were manufactured inside dying stellar cores. The oxygen flowing through your lungs originated when colossal stars detonated in cosmic explosions surpassing human imagination, spreading their atomic offspring throughout galaxies like celestial seeds destined to become worlds, organisms, and conscious awareness. Every single particle composing your being carries the status of cosmic wanderer, catastrophe survivor, and witness to the universe's 14 billion-year evolution, from basic simplicity toward breathtaking complexity. Hydrogen molecules in your morning beverage retain memories from when our cosmos was merely 20 minutes old. The heavier elements constructing your skeleton and bloodstream carry experiences of stellar deaths and resurrections, participating in recycling processes, operating across spatial and temporal scales that render human civilization microscopic. Tonight's adventure will trace this incredible odyssey step by careful step. We'll begin at absolute zero, during initial moments when universal temperatures and density prevented atomic existence entirely. During this primordial epoch, matter and energy engaged in cosmic choreography, involving continuous creation and destruction cycles. We'll observe universal expansion and cooling, witnessing conditions emerge where atomic nuclei could finally form and maintain stability. We'll experience the cosmic dark period when space filled with exposed nuclear cores and liberated electrons, maintaining temperatures too extreme for stable atoms while remaining opaque to electromagnetic radiation, shrouded in impenetrable cosmic haze. Then comes the miraculous moment of cosmic sunrise when universal cooling finally permitted electrons and nuclei to unite into the first electrically neutral atoms, enabling light to journey freely through space for the very first time. This narrative extends beyond ancient historical events. It encompasses the continuing marvel of atomic durability, the precise equilibrium of forces, allowing surrounding matter to preserve structural integrity across cosmic timescales. We're exploring quantum mechanical principles, preventing electrons from collapsing into atomic centers, nuclear physics, maintaining proton and neutron bonds despite natural repulsion, and electromagnetic interactions enabling atoms to connect into molecules, constructing complex chemical processes essential for biological existence. We're launching into existence's greatest investigative mystery, utilizing evidence encoded in stellar radiation and cosmic background signals to reconstruct events occurring when our universe was younger than a single human pulse. You'll discover how researchers assembled this remarkable chronicle through methodical observations, brilliant theoretical breakthroughs, and laboratory experiments recreating conditions from creation's opening moments. The pathway ahead challenges your fundamental assumptions about temporal flow, spatial dimensions, matter composition, and energy behavior. We'll encounter ideas that appear to contradict everything you believed about causation and consequence. We'll explore domains where conventional physics laws dissolve completely, discovering that existence proves far more bizarre and magnificent than anyone imagined just 1 century ago. But here's the most astounding aspect. This isn't merely academic study or abstract information collection. This represents your personal Genesis account, the complete explanation of how you individually came into existence. Not simply how your ancestors met or how terrestrial life developed, but how the fundamental particles constructing your physical form originated from absolute void and assembled through cosmic mechanisms into the thinking, feeling, questioning consciousness experiencing these words right now. So settle comfortably, breathe deeply that ancient hydrogen mixed with stellar oxygen, and prepare for mental expansion through the most incredible factual narrative ever uncovered. The complete story of atomic formation from nothingness, how existence emerged from void, and how emptiness revealed itself far more fascinating than anyone previously suspected. Our universe prepares to unveil its most profound mysteries, granting you premium seating for existence's greatest performance. Let's commence our journey backward to everything's absolute beginning. Our chronicle opens in conditions so extreme they shatter every intuition we've developed regarding reality's fundamental operations. We're examining the initial fleeting instance, following the Big Bang, when our entire observable universe compressed into dimensions smaller than a proton, heated to temperatures making the hottest stellar cores seem like Arctic wasteland. Envision this impossibility, everything visible in all directions, extending as far as humanity's most powerful telescopes can detect, squeezed into a point so microscopic that comparing it to an atom resembles comparing a sand grain to our entire planet. Temperatures during this moment reached levels our consciousness simply cannot comprehend. We're discussing 10 to the 32nd power Kelvin, a numeral 1, followed by 32 zeros, representing heat intensity. These conditions were so extreme that matter and energy concepts became completely meaningless. Under these incomprehensible circumstances, fundamental forces governing today's universe existed as a unified primordial superforce. Gravity, electromagnetism, strong nuclear interaction, and weak nuclear interaction, all the players eventually choreographing atomic cosmic ballet remained indistinguishable from each other. Imagine having every symphony orchestra instrument performing identical notes at volumes capable of shattering reality itself. But here's where our story becomes even more consciousness-bending. This wasn't simply hot and dense conditions. This represented an existence state where normal temporal flow itself breaks down completely. Our finest theories suggest that time as we understand it might not have existed meaningfully whatsoever. Mathematical descriptions of these opening moments predict what physicists term a singularity, a point where equations literally collapse, producing infinite values. Most physicists don't believe our universe actually achieved infinite density and temperature. Instead, they suspect current physics understanding simply isn't sophisticated enough for describing what genuinely occurred at absolute beginning. We need theoretical frameworks successfully combining quantum mechanics, governing incredibly small behaviors, with general relativity, describing gravitational effects and large-scale space-time structure. However, here's what we know with remarkable confidence. Something extraordinary occurred around 10 to the negative 36 seconds after commencement. That represents a decimal point, followed by 35 zeros, then the digit 1. During this moment, our universe underwent what cosmologists call cosmic inflation, the most rapid expansion in existence history. Within a time span so brief it makes eye-blinking seem eternal, universal expansion occurred by factors staggering imagination. We're describing growth from subatomic particle dimensions to approximately grapefruit size. This entire transformation occurred faster than finger-snapping. In reality, this expansion proceeded so rapidly that it surpassed light velocity, something sounding impossible until you realize matter wasn't moving through space, but space itself was stretching. This cosmic inflation resolves one of the most perplexing observations about our universe. When we examine all directions around us, we observe cosmic microwave background radiation, the Big Bang's afterglow, maintaining virtually identical temperatures everywhere we look. This appears impossible, because spatially separated regions should never have communicated with each other, never having enough time to achieve thermal equilibrium, but inflation resolves this puzzle elegantly. Before inflation, all these apparently disconnected zones were actually in intimate contact. able to reach uniform temperature before being stretched apart by explosive expansion. As inflation concluded around 10 to the negative 32nd seconds, our universe entered what physicists call the electro-weak epoch. Temperature had declined to a nearly incomprehensible 10 to the 15th power Kelvin, cool enough for the unified superforce to begin fragmenting. The strong nuclear force separated first, followed by electromagnetic and weak forces breaking apart from each other. This separation wasn't merely abstract cosmic reorganization. It marked the moment when reality's fundamental architecture, as we know it, began taking shape. The forces that would eventually enable protons to stick together in atomic nuclei, permit electrons to orbit those nuclei without spiraling inward, and enable complex chemistry essential for life itself, all began assuming their distinct identities. But we still lack atoms. We don't even possess atomic building blocks yet. Temperature remains so extreme that even protons and neutrons cannot exist as stable entities. Instead, our universe fills with what physicists term quark-gluon plasma, a seething ocean of the most fundamental particles we understand, held together by forces so intense they defy description. Quarks represent the building blocks of protons and neutrons. However, in this early cosmic furnace, they cannot combine into these familiar particles. Temperature is simply too high, energy too intense. It resembles attempting to construct a house during a tornado made of fire. Every time quarks attempt binding together through strong nuclear force, thermal violence tears them apart again. Gluons, meanwhile, are force-carrying particles that mediate strong nuclear force. They're the cosmic adhesive that will eventually hold quarks together inside protons and neutrons. But at these temperatures, even they cannot establish stable connections. The entire universe resembles cosmic soup where matter's ingredients exist, but cannot yet combine into anything we would recognize as substantial. As universal expansion continues, cooling also continues. This isn't gentle cooling you might experience stepping outside on winter evenings. This represents fundamental transformation in reality's nature itself. As available energy drops below critical thresholds, new organizational forms can emerge. Around 1 microsecond after the Big Bang, when temperature has fallen to approximately 10 to the 13th power Kelvin, something remarkable occurs. Our universe finally becomes cool enough for quarks to bind together into protons and neutrons. This transition, called the QCD phase transition, marks the birth of particles that will form all future atomic nuclei. Picture this moment as cosmic alchemy on unimaginable scales. Suddenly, chaotic quark-gluon plasma begins organizing itself into discrete packages. 2 up quarks and 1 down quark bind together, forming protons, each carrying positive electric charge. 2 down quarks and 1 up quark combine, creating neutrons, electrically neutral but slightly more massive than their proton cousins. This mass difference between protons and neutrons, tiny though it is, will prove crucial for universal future development. It's one of those seemingly minor details that turns out having cosmic significance, determining eventual hydrogen to helium ratios throughout the universe, and setting stages for stellar formation billions of years ahead. The strong nuclear force binding quarks together inside protons and neutrons operates unlike anything we encounter in everyday experience. It actually grows stronger as quarks are pulled apart, rather than weaker like every other force we know. Try separating quarks beyond certain distances, and required energy becomes so intense, it creates new quark-anti-quark pairs rather than achieving separation. It's as if existence itself refuses allowing quarks to exist in isolation. But even with protons and neutrons now populating the cosmic scene, we still cannot have atoms. Temperature remains far too high for electrons to remain bound to nuclei. Any electron attempting to settle into orbit around a proton gets immediately blasted away by intense thermal radiation filling space. Our universe at this stage resembles a cosmic storm of naked atomic nuclei and free electrons all bouncing around in violent thermal motion. The electrons themselves present their own fascinating story. Unlike protons and neutrons, which are composed of quarks, electrons appear to be fundamental particles with no detectable internal structure. They're point-like entities carrying electric charge and spin, participating in electromagnetic and weak nuclear forces, but remaining immune to strong force binding quarks together. These electrons were created earlier in the cosmic timeline through processes that transformed pure energy into matter and antimatter pairs. For every electron created, an antimatter twin called a positron also came into existence. In a perfectly symmetric universe, all these particles and antiparticles should have annihilated each other completely, leaving nothing but pure energy behind. But our universe harbors subtle asymmetry, a slight preference for matter over antimatter, that remains one of physics' deepest mysteries. For every billion antimatter particles created in the early universe, there were approximately 1,000,000,001 matter particles. This tiny imbalance, this cosmic rounding error, is the reason anything exists at all. After all, matter and antimatter annihilated each other in spectacular bursts of gamma radiation. That leftover fraction of matter particles remained to build everything we observe today. The scale of this annihilation was beyond anything we can readily comprehend. Imagine every particle in the observable universe paired with an antiparticle twin, both vanishing in pure energy release. Our universe was literally illuminating itself from within, converting mass into radiation in quantities that dwarf the output of every star that has ever shone. This cosmic light show represents one of the most violent and spectacular events in universal history, yet it left behind just enough matter to eventually become galaxies, stars, planets, and conscious beings capable of contemplating their own origins. The mathematical precision required for this delicate balance staggers the imagination. Had the matter-antimatter asymmetry been even slightly different, say, 1 part in 10 billion instead of 1 part in a billion, our universe would either contain no matter at all, or would have collapsed back on itself before stars could form. We exist because of a cosmic coincidence, so improbable it challenges our understanding of chance itself. Yet through this cosmic conflagration, that precious remnant of matter survived. The electrons that would eventually orbit atomic nuclei, the protons that would form hydrogen atoms, the neutrons that would enable the creation of heavier elements. All of them are survivors of this primordial holocaust, the victors in a battle between existence and oblivion that was decided by the slimmest of margins. As our universe continued its relentless expansion and cooling, we approach another crucial threshold in our story. Temperature is dropping toward levels where atomic nuclei can begin to form, where protons and neutrons can stick together despite electromagnetic repulsion between positively charged protons. This process, called Big Bang nucleosynthesis, represents our universe's first attempt at chemistry, though it's chemistry unlike anything you'd recognize from your high school textbook. Instead of gentle molecular interactions, we're dealing with nuclear processes that require temperatures of billions of degrees, energies that can overcome fundamental forces holding matter apart. The neutrons, unstable when left alone, begin decaying into protons through a process mediated by weak nuclear force. A neutron transforms into a proton, an electron, and a nearly massless particle called a neutrino. This decay would eventually eliminate all neutrons from our universe if they couldn't find partners. But the high-energy environment allows some neutrons to bind with protons before they can decay. When a proton and neutron successfully combine, they form the nucleus of heavy hydrogen called deuterium. This is an incredibly delicate process, requiring precise conditions of temperature and density. Too hot and thermal radiation tears the newly formed nucleus apart before it can stabilize. Too cool, and particles lack the energy needed to overcome their mutual repulsion and bind together. Our universe threads this needle with exquisite precision, creating a window of opportunity lasting only a few minutes during which nuclear synthesis can occur. In this brief cosmic moment, roughly 25% of all protons in our universe combine with neutrons to form helium nuclei, each containing 2 protons and 2 neutrons bound together by strong nuclear force. Smaller amounts of deuterium, tritium, and lithium also form during this period, but the expanding universe cools too quickly for more complex nuclei to assemble. The process grinds to a halt when temperature drops below the threshold needed for nuclear fusion, leaving our universe with a specific mixture of light elements that matches observations with startling accuracy. This cosmic cooking session lasts only about 20 minutes, but its products will endure for billions of years. The helium created during Big Bang nucleosynthesis still comprises roughly 25% of all ordinary matter in our universe today, exactly as predicted by our theoretical models. It's one of the great triumphs of modern cosmology, a precise quantitative prediction that matches observation across the entire observable universe. But we still don't have atoms. We have atomic nuclei swimming in a sea of free electrons, but temperature is still too high for these components to combine into neutral atoms. Our universe remains opaque to light, a cosmic fog where photons can't travel more than a tiny distance before being scattered by free electrons. This fog-bound era will persist for hundreds of thousands of years, a cosmic dark age when our universe was filled with matter, but remained invisible to any hypothetical observers. The stage is set for atomic formation. All the players are in position, but the final act of our cosmic drama must wait for our universe to cool just a little bit more. The atoms that will eventually form your body, that will become the air you breathe and the ground beneath your feet, are still centuries of millennia away from their moment of birth. But the foundation has been laid. The nuclear building blocks are in place, and our universe continues its patient expansion toward the moment when electrons and nuclei can finally unite in stable neutral atoms. That moment, when it comes, will flood our universe with light for the first time, marking the end of the cosmic dark ages and the beginning of the era when matter can begin organizing itself into complex structures that will eventually give rise to stars, planets, and life itself. The cosmic clock keeps ticking, and we're approaching one of the most extraordinary moments in existence history. Picture our universe as it exists roughly 400,000 years after the Big Bang. It's still unimaginably hot by earthly standards, hovering around 3000 degrees Kelvin, but this represents dramatic cooling from those first blazing moments we just witnessed. At this temperature, something magical is about to happen. For the first time since our universe began, conditions are becoming just right for electrons and atomic nuclei to dance together in stable partnerships. We're about to witness the birth of the very first atoms, and with them the transformation of our cosmos from an opaque, fog-shrouded realm into a transparent universe where light can finally travel freely across vast distances. This moment has a beautiful name in cosmology: recombination. Though technically it should be called combination, since electrons and nuclei are meeting for the first time rather than reuniting. But the name has stuck, and there's something poetic about it. After hundreds of thousands of years of separation, the fundamental building blocks of matter are finally ready to recombine into something greater than the sum of their parts. Before this moment, every photon in our universe was trapped in an endless game of cosmic pinball. Light couldn't travel more than a few meters before colliding with a free electron, getting scattered in a random direction, only to immediately hit another free electron and bounce again. Our universe was like cosmic fog so thick that even if stars had existed, which they didn't, you wouldn't have been able to see your hand in front of your face. But as temperature drops below that critical threshold of 3000 Kelvin, electrons begin losing their frantic thermal energy. They're no longer moving fast enough to escape when they wander close to the electromagnetic pull of an atomic nucleus. It's like watching cosmic snowflakes form as our universe cools, with electrons settling gently into stable orbits around protons and helium nuclei. The process doesn't happen all at once across the entire universe. Instead, it unfolds like a wave of organization spreading through space, transforming chaos into order one atom at a time. In regions where density is slightly higher, recombination occurs first. In emptier regions, it takes a bit longer. This cosmic transformation marks humanity's earliest observable moment in universal history. Before recombination, our universe was opaque to electromagnetic radiation. The constant scattering of photons by free electrons created what physicists call a photon barrier that prevents us from directly observing anything that happened earlier. But once recombination began, photons could finally travel freely without constant interference. Those first photons released during recombination are still traveling through space today. We detect them as the cosmic microwave background radiation, the afterglow of creation itself. This ancient light carries information about conditions when our universe was only 400,000 years old, providing our most direct evidence of what happened during those crucial early moments. The cosmic dark ages were finally ending. Light could travel unimpeded for the first time, setting the stage for the next chapter in our universe's evolution. Soon, gravity would begin pulling matter together into the first stars and galaxies. But that's another story. For now, we celebrate this moment when atoms were born from nothing, when electrons and nuclei found each other in the cosmic dance that makes all chemistry, all life, all consciousness possible. This slight variation in timing will prove crucial billions of years later, when these density differences grow into the cosmic web of galaxies and empty voids that structure our universe today. When that first hydrogen atom forms, when that first electron settles into its quantum mechanical dance around a proton, something unprecedented occurs. The photon that had been bouncing between free charges suddenly finds itself in a universe where most electrons are bound up in neutral atoms. With dramatically fewer free electrons to scatter off, light can finally travel in straight lines across cosmic distances. This liberation of light marks one of the most significant transitions in cosmic history. In a relatively brief period, cosmically speaking, our universe transforms from opaque to transparent. The cosmic microwave background radiation that we detect today is the afterglow of this moment, the last light scattered by free electrons before atoms formed, and the fog lifted forever. But let's focus on those first atoms themselves, because they're about to become the protagonists of our story. The hydrogen atom, consisting of a single proton embraced by a single electron, becomes our universe's most abundant creation. These simple atoms make up roughly 75% of all ordinary matter that will ever exist. Every hydrogen atom in your body, in the water you drink, in the vast interstellar clouds between stars, traces its lineage back to these first moments of atomic formation. The helium atoms tell an equally fascinating story. With 2 protons and 2 neutrons in their nuclei, they require 2 electrons to achieve neutrality. These more complex atoms represent about 25% of ordinary matter, and their formation during recombination creates the first examples of what we might call atomic diversity. Our universe is no longer monotonous. It now contains 2 distinct types of atoms, each with its own unique properties and potential for future chemistry. There's something almost miraculous about quantum mechanics that allow these first atoms to remain stable. Classical physics would predict that electrons should spiral into the nucleus, radiating energy and causing atoms to collapse in a tiny fraction of a second. But quantum mechanics saves the day with its strange rules about allowed energy levels and the uncertainty principle. Each electron in an atom can only exist in specific quantized energy states. It's as if our universe has invisible steps built into it, and electrons can only stand on these steps, never between them. The lowest step, called the ground state, represents a perfect balance between the electron's kinetic energy and its attraction to the nucleus. The electron literally cannot fall any lower, because there is no lower energy level available to it. This quantum mechanical stability is what makes chemistry possible. Without it, atoms would be fleeting, unstable entities that could never persist long enough to combine into molecules, let alone complex structures like proteins or DNA. Our universe would remain forever simple, forever boring, forever incapable of generating the complexity that leads to stars, planets, and eventually consciousness itself. As recombination sweeps across the cosmos, we're witnessing our universe's first great phase transition. Since the moments immediately after the Big Bang, the change is as dramatic as water freezing into ice. But instead of a change in molecular arrangement, we're seeing a fundamental transformation in matter's very nature itself. The newly formed atoms don't just sit there passively, they immediately begin interacting with each other through gravitational attraction. Remember, gravity is an incredibly weak force on atomic scales, but it's also the only force that acts over truly cosmic distances without diminishing. Every hydrogen atom pulls on every other hydrogen atom, no matter how far apart they are. These gravitational interactions are almost imperceptibly tiny at first, but they're persistent and cumulative. Regions of space that happen to have slightly more matter than average begin attracting additional matter from their surroundings. Over millions of years, these tiny density fluctuations will grow into the seeds of cosmic structure, the birthplaces of the first stars. But we're getting ahead of ourselves. For now, let's appreciate what has just occurred. Our universe has just become a place where stable matter can exist, where the fundamental building blocks of complexity have taken their first tentative steps toward organization. We have atoms, real atoms, with electrons orbiting nuclei in stable configurations that will persist for billions of years. These atoms are still incredibly simple by the standards of what's to come. We have hydrogen and helium, period. No carbon, no oxygen, no iron, no silicon. None of the heavier elements that will eventually make planets possible, that will enable the rich chemistry of life. Those elements are still locked away in the future, waiting to be forged in nuclear furnaces of the first stars. But even these simple atoms represent a monumental achievement. They are our universe's first successful attempt at building stable complex structures from simpler components. They demonstrate that the laws of physics, those fundamental rules governing how particles interact, are capable of generating order from chaos, complexity from simplicity, something from nothing. The electromagnetic force that holds electrons in their atomic orbits is the same force that will eventually enable atoms to link together into molecules. The quantum mechanical rules that stabilize these first atoms will govern all future chemistry. The gravitational attraction between atoms will grow into the force that builds stars and galaxies. In these first atoms we can already see the seeds of everything that will follow. The hydrogen that will fuel the first stars, providing the energy source that powers stellar nucleosynthesis and creates heavier elements. the helium that will serve as the end product of hydrogen fusion, signaling when stars have exhausted their primary fuel source, the gravitational clumping that will eventually pull matter together into dense cores where nuclear fusion can ignite. Our universe has just taken its first major step toward becoming the rich, complex, fascinating cosmos we inhabit today. From a state where stable matter was impossible, we've transitioned to a realm where atoms can exist indefinitely, where the building blocks of complexity are finally available for construction projects that will span cosmic time. This is the moment when our universe stops being just about fundamental physics and starts becoming about chemistry, about structure, about the endless possibilities that emerge when simple components combine in creative ways. We're still hundreds of millions of years away from the first stars, billions of years from the first planets, but the foundation has been laid. The atoms floating through space in the aftermath of recombination don't know that they're destined to become part of stellar cores, planetary atmospheres, or eventually the bodies of conscious beings who will contemplate their own atomic origins. They're just following the laws of physics, responding to forces, moving through space according to gravitational choreography that will shape cosmic evolution. But we know their future, and it's spectacular. These simple atoms born in the cooling aftermath of the Big Bang will participate in cosmic processes that transform them into every element on the periodic table. They'll witness the birth and death of stars, the formation of galaxies, the emergence of planets capable of harboring life. Some of these very atoms, the ones forming right now in our cosmic narrative, will eventually find themselves incorporated into your body, carrying the memory of recombination in their quantum mechanical structure. Every breath you take connects you to this primordial moment when atoms first formed from nothing. Every thought racing through your mind exists because of quantum mechanical rules that first stabilized electrons in atomic orbits nearly 14 billion years ago. This is your story. This is how you came to exist. Not just your biological evolution or your family history, but the fundamental narrative of how the particles comprising your very essence emerged from absolute void and assembled through cosmic processes spanning universal history. You are made of atoms that remember the universe's earliest moments, that carry within their structure the signature of cosmic recombination, the echo of creation itself. Welcome to your cosmic heritage. Welcome to the extraordinary truth that you are literally made of stardust and quantum mechanics, of primordial hydrogen and ancient helium, of forces and fields that emerged from nothing and became everything. This is the most incredible true story ever discovered. The story of how atoms formed from nothing, how something came from nothing, and how that nothing turned out to be far more interesting than anyone ever imagined. The hydrogen in your water molecules, the helium that was once dissolved in your bloodstream during a medical procedure, they all trace their existence back to this moment when electrons and nuclei first found each other in the cooling universe. We're witnessing the birth of atomic matter as a permanent feature of cosmic architecture. Before this moment, atoms were impossible. After this moment, they become the fundamental currency of cosmic complexity, the building blocks from which everything else will be constructed. Our universe has just learned how to make atoms from nothing, and it will never forget this lesson. From this point forward, atomic matter will be a persistent feature of reality, the foundation upon which all future complexity will be built. The age of atoms has begun, and with it, our universe has taken its first major step toward becoming the magnificent, complex, life-bearing cosmos we call home. Now, as these first atoms drift through cosmic darkness, something extraordinary begins to unfold. Our universe has just learned its first lesson in construction, but it's about to discover that atoms are merely the opening chapter in a much grander story of creation. Picture the cosmos at this moment. We're roughly 400,000 years past the Big Bang, and space stretches endlessly in all directions, filled with a thin soup of hydrogen and helium atoms. Temperature has dropped to a mere 3,000 degrees Kelvin, practically Arctic compared to those first blazing moments. But this cooling universe is far from dormant. It's pregnant with potential, ready to give birth to structures that will dwarf anything we've seen so far. The atoms floating through this primordial space aren't distributed evenly. Quantum fluctuations from the inflationary epoch have left their fingerprints on the cosmic fabric, creating regions where matter is slightly more concentrated, and others where it's slightly more sparse. These density variations are incredibly subtle, differences of only 1 part in 100,000, but they represent the seeds from which cosmic architecture will grow. Gravity, that patient sculptor of our universe, begins its slow but inexorable work. Every atom pulls on every other atom with a force so weak it seems almost negligible, But gravity has two crucial advantages over every other force in nature. It never stops pulling, and it never gets tired. While electromagnetic forces can be shielded, and nuclear forces operate only at microscopic scales, gravity reaches across the vast emptiness of space with infinite patience and unlimited endurance. In those regions where atoms happen to be slightly more concentrated, gravitational attraction begins to win a cosmic tug-of-war. More matter attracts even more matter in a process that feeds on itself. It's like watching cosmic snowballs grow as they roll downhill, gathering more material with each passing millennium. But this isn't the gentle accumulation you might imagine. We're dealing with processes that operate across scales so vast, they challenge human comprehension. Individual atoms might drift for millions of years before encountering enough neighbors to feel significant gravitational pull. Our universe has all the time in existence to work with, and it uses every second. As these gravitational seeds continue to grow, they begin carving structure into what was once smooth space. Matter flows along invisible highways of gravitational attraction, creating a cosmic web of filaments and voids that will persist for billions of years. Our universe is learning architecture, discovering how to build with atoms the way a master craftsman learns to work with wood or stone. The process accelerates as matter becomes more concentrated. Gravitational attraction grows stronger as more atoms cluster together, pulling in material from ever greater distances. What started as barely perceptible density fluctuations evolve into genuine concentrations of matter, protogalactic clouds that span hundreds of thousands of light years. Inside these growing clouds, something remarkable happens. As atoms fall inward under their mutual gravitational attraction, they begin to speed up. The gravitational potential energy of their elevated positions converts into kinetic energy of motion. The atoms start moving faster, colliding more frequently, and most importantly, heating up. This heating represents a fundamental transformation in cosmic evolution's nature. For the first time since recombination, thermal energy begins to compete with the cooling expansion of our universe. Local regions of space start getting warmer rather than cooler, setting the stage for processes that require enormous temperatures to operate. The hydrogen and helium atoms spiraling inward in these collapsing clouds don't realize they're participating in one of the most crucial transitions in cosmic history. They're simply following physics laws, responding to gravitational forces, converting potential energy into kinetic energy, according to rules established in the first moments after the Big Bang. But we can see where this process is heading. These atoms are unwittingly constructing furnaces that will forge every other element in the periodic table. They're building stellar nurseries where nuclear fusion will transform hydrogen into helium, helium into carbon, carbon into oxygen, and so on up the atomic ladder to create the rich diversity of elements that makes complex chemistry possible. The collapse continues for millions of years, with matter streaming inward from distances measured in light years. Temperatures in the densest regions climb from 3,000 Kelvin to 10,000, then 100,000, then 1,000,000 degrees. The atoms that once drifted peacefully through empty space now find themselves in an increasingly violent thermal environment. At these rising temperatures, something fascinating begins to happen to atomic structure itself. The electrons that had settled so comfortably into their quantum mechanical orbits around nuclei start getting excited into higher energy states. Collisions between atoms become energetic enough to knock electrons completely free from their nuclei, reversing the process of recombination that had occurred hundreds of millions of years earlier. But this isn't a return to the cosmic fog of the early universe. This time, ionization is localized, confined to specific regions where gravitational collapse has concentrated matter and raised temperatures. Our universe is developing structure, creating places where conditions are dramatically different from the cold emptiness of intergalactic space. As collapse continues and temperatures soar even higher, we approach another critical threshold. When core temperature of these collapsing clouds reaches roughly 10 million Kelvin, something extraordinary occurs. The thermal energy becomes so intense that it can overcome electromagnetic repulsion between atomic nuclei. Hydrogen nuclei, which are just lone protons, begin moving fast enough to crash into each other with sufficient force to trigger nuclear fusion. This isn't the gentle chemistry of electron-orbital interactions we saw during recombination. This is nuclear alchemy, the transformation of one element into another, through processes that release enormous amounts of energy. When 4 hydrogen nuclei manage to combine into a single helium nucleus through a complex series of reactions, they release energy in the form of gamma radiation, positrons and neutrinos. But here's the crucial detail that makes stellar fusion possible. The mass of the helium nucleus is slightly less than the combined mass of the 4 hydrogen nuclei that created it. That missing mass doesn't simply disappear. According to Einstein's famous equation, E=mc², it converts directly into energy. A tiny amount of matter becomes a tremendous amount of energy, enough to power stellar fusion reactions for billions of years. This energy release creates radiation pressure that pushes outward against the inward pull of gravity. For the first time in cosmic history, we have a force capable of balancing gravitational collapse. The result is a stable, self-regulating system where nuclear fusion generates exactly enough outward pressure to counteract gravitational compression. Congratulations, our universe has just ignited its first star. This moment represents a phase transition as dramatic as anything we've witnessed in our cosmic journey so far. From a universe containing only hydrogen and helium atoms floating in darkness, we've reached a point where nuclear furnaces begin forging heavier elements, where gravity has learned to kindle cosmic fires that will burn for billions of years, where the stage is finally set for the rich chemical complexity that makes planets, life, and consciousness possible. The first star marks the end of our cosmic dark ages, and the beginning of an era of light, heat, and elemental creation. From atoms that formed from nothing, gravity has constructed engines of stellar nucleosynthesis that will populate our universe with every element needed for the complexity we see today. This is how something truly magnificent emerged from absolutely nothing, through patience, precision, and the inexorable pull of fundamental forces operating across cosmic time. We've transitioned from a cosmos filled with elementary atoms floating through vacant space to one where nuclear reactors blaze at temperatures of millions of degrees, transforming hydrogen into helium and unleashing the energy that will make all future complexity achievable. But the ignition of the first star is merely the opening of stellar nucleosynthesis, the procedure that will fill the periodic table with elements more massive than hydrogen and helium. Within stellar hearts, where temperatures climb to tens of millions of degrees and pressures surpass anything conceivable on Earth, atomic nuclei engage in a cosmic culinary process that generates the chemical variety essential for planets, life, and consciousness. The helium produced by hydrogen fusion doesn't remain inactive. In the most colossal stars, core temperatures eventually become scorching enough for helium nuclei to merge together, producing carbon in a procedure that demands 3 helium nuclei to impact almost simultaneously. This triple alpha procedure, as physicists term it, is so unlikely that it appears miraculous it happens at all, yet happen it does, and the carbon nuclei manufactured by helium fusion become the raw materials for even more extraordinary nuclear reactions. Carbon can merge with helium to generate oxygen. Oxygen can unite with helium to manufacture neon. The stellar foundry continues advancing up the periodic table, producing silicon, sulfur, phosphorus, and eventually iron. Each stage in this nucleosynthetic ladder demands higher temperatures and pressures than the previous. The star must consume through its fuel reserves in successive layers, first transforming hydrogen to helium in its heart, then helium to carbon when the hydrogen is depleted, then carbon to heavier elements in an increasingly desperate attempt to sustain the energy production needed to prevent gravitational collapse. The atoms being manufactured in these stellar foundries have no awareness. They're contributing to the genesis of cosmic complexity. They're simply reacting to the extreme conditions inside stellar hearts, obeying the laws of nuclear physics, wherever those laws guide them. But we can recognize the profound importance of what's happening. Every carbon atom that will eventually become part of your DNA is being manufactured right now in these first stellar hearts. Every oxygen atom that you'll inhale, every calcium atom that will fortify your bones, every iron atom that will transport oxygen in your bloodstream, all of them are products of stellar nucleosynthesis, occurring in the first generation of stars. This procedure continues for millions of years, with each star serving as a cosmic chemistry laboratory, converting the simple hydrogen and helium remaining from the Big Bang into the rich variety of elements that will make planets and life achievable. But stellar nucleosynthesis encounters a fundamental restriction that will prove crucial for the future development of cosmic complexity. Iron represents a nuclear dead end. Elements lighter than iron release energy when they merge together, providing the fuel that powers stellar reactions. But iron nuclei are so tightly bound that merging them together actually demands energy rather than releasing it. When a massive star's heart fills with iron, nuclear fusion can no longer produce the radiation pressure needed to balance gravitational collapse. What occurs next is one of the most violent events in the universe. A core collapse, supernova. The iron heart, no longer supported by fusion reactions, collapses in a fraction of a second from the size of Earth to the size of a city. The gravitational energy released by this collapse is so enormous that it reverses the infall and explodes the star apart in an explosion that briefly outshines an entire galaxy. But this stellar death serves a crucial purpose in cosmic development. The supernova explosion generates conditions even more extreme than stellar hearts, temperatures and pressures sufficient to manufacture elements heavier than iron through rapid neutron capture procedures. Gold, platinum, uranium, and all the other elements beyond iron in the periodic table are generated in these moments of stellar destruction. More importantly, the supernova blast wave hurls all the elements produced during the star's lifetime out into space, seeding the interstellar medium with the chemical variety necessary for future planet formation. The carbon, oxygen, silicon, and iron that took millions of years to generate in stellar hearts are scattered across light years of space in a matter of hours. This element dispersal represents another crucial phase transition in cosmic development. We've transitioned from a cosmos containing only hydrogen and helium to one where space itself is enriched with the full spectrum of elements needed for rocky planets, complex chemistry, and eventually life itself. The atoms blown into space by supernova don't remain isolated for long. Gravity continues its patient work, pulling this enriched material back together into new generations of stars. And for the first time in cosmic history, planetary systems, the second and third generation stars that form from this enriched material, have access to the full periodic table, enabling them to develop the solid planets, where complex chemistry can occur. Our universe has learned how to make atoms from nothing, how to build stars from atoms, how to manufacture new elements in stellar hearts, and how to distribute those elements through space via stellar explosions. Each stage in this procedure has opened up new possibilities for complexity, new ways for matter to organize itself into increasingly sophisticated structures. We're now roughly 1 billion years past the Big Bang, and the cosmos has become almost unrecognizably complex compared to those first moments when even atoms were impossible. We have galaxies filled with billions of stars, planetary systems with rocky worlds, and interstellar space enriched with every element necessary for the chemistry of life. But the story of atomic formation is far from over. Those elements scattered by dying stars will eventually condense into new worlds where atoms can experiment with molecular combinations impossible in the extreme environments of stellar hearts. They'll discover how to build proteins and DNA, how to generate the complex molecular machinery that enables life to emerge from non-living matter. The atoms in your body right now are veterans of this cosmic journey. They've survived the violence of stellar hearts, the explosive fury of supernova, the patient accumulation of planetary formation, and billions of years of geological and biological development. They carry within their quantum mechanical structure the entire history of our universe, from the first moments after the Big Bang to the present day. You are tonight, as you contemplate these words, you're not just learning about atomic formation, you're communing with our universe's deepest creative procedures, recognizing your intimate connection to cosmic development itself. The atoms that make up your thoughts, the ones processing these ideas right now, they're not separate from our universe's story of creation. They are that story living and breathing and thinking its way toward ever greater complexity and understanding. Our universe has just discovered something profound about itself. It has learned that destruction can be an act of creation, that violence can serve beauty, that endings can become beginnings on scales that dwarf human imagination. Those scattered atoms hurled across space by dying stars carry with them the potential to build worlds we can barely comprehend. Picture this cosmic recycling program, operating on timescales that make geological epochs seem like heartbeats. The carbon manufactured in stellar hearts drifts through space for millions of years, joining vast molecular clouds that span hundreds of light years. These aren't the empty voids you might imagine when you think of outer space. They're cosmic nurseries rich with the chemical variety that makes complexity achievable. In these interstellar clouds, atoms encounter conditions they've never experienced before. Temperature drops to just a few degrees above absolute zero, so cold that even helium freezes solid. Density is so low that a cubic meter might contain fewer atoms than a single breath of air on Earth. Yet, in this seemingly barren environment, something remarkable begins to happen. For the first time since those early moments after the Big Bang, atoms have the opportunity to engage in gentle chemistry rather than violent nuclear reactions. This marks the beginning of molecular complexity, where atoms learn to dance together in intricate partnerships that will eventually lead to the chemistry of life itself. From nothing came atoms, from atoms came stars, from stars came elements, and from elements will come the molecular machinery that makes consciousness possible. The cosmic story continues, and you are both its narrator and its most extraordinary creation. Without the crushing pressures and searing temperatures of stellar hearts, electrons can once again perform their delicate choreography around atomic nuclei, forming the chemical bonds that will eventually enable molecular complexity. Hydrogen atoms, our universe's most abundant creation, begin linking up with other elements to form simple molecules. Water emerges when hydrogen meets oxygen, creating H2O molecules that will eventually become the solvent for life's chemistry. Carbon monoxide develops from the marriage of carbon and oxygen, while hydrogen cyanide brings together hydrogen, carbon and nitrogen in combinations that hint at the organic chemistry to come. These molecular formation procedures occur with exquisite slowness compared to the nuclear furnaces of stars. Individual atoms might drift through space for thousands of years before encountering the right partner for a chemical reaction. But our universe has patience, and these interstellar clouds have lifespans measured in tens of millions of years. As more complex molecules form, they begin to stick to tiny grains of cosmic dust, creating microscopic laboratories where surface chemistry can occur. These dust grains, smaller than the wavelength of visible light, serve as meeting places where atoms can encounter each other more frequently than they would in the vast emptiness of space. On the surfaces of these dust grains, protected from the harsh radiation that would destroy them in open space, molecules can grow in complexity. Simple two-atom combinations link up to form chains and rings, creating the first organic compounds to exist since our universe began. Methane, ammonia, and even more complex hydrocarbons begin to populate these molecular clouds. But we're still discussing incredibly simple chemistry compared to what's coming. These early molecules are like the first hesitant words in a language that will eventually produce poetry and philosophy. They represent our universe's initial experiments with the kinds of chemical bonds that will one day enable DNA to store information and proteins to catalyze the reactions of life. The gravitational story we witnessed earlier with star formation repeats itself on smaller scales within these molecular clouds. Dense regions begin attracting material from their surroundings. But this time the collapsing matter includes not just hydrogen and helium, but the full spectrum of elements created by stellar nucleosynthesis. As these enriched regions contract under their own gravity, something unprecedented becomes possible. Instead of all the infalling matter ending up in a central star, some of it remains in orbit, forming a flattened disk of gas and dust surrounding the nascent stellar system. This protoplanetary disk contains all the ingredients necessary for rocky planet formation. In the cooler outer regions of these disks, water and other volatile compounds can exist as solid ice. Closer to the forming star, where temperatures are higher, only rocky materials can remain solid. This temperature gradient creates distinct zones where different types of worlds can form. From rocky terrestrial planets near the star to gas giants in the outer system, the process of planet formation represents another phase transition in our universe's growing complexity. Tiny dust grains begin sticking together through electrostatic forces, growing into pebbles, then boulders, then planetesimals kilometers across. These building blocks of worlds collide and merge in a chaotic dance of gravitational attraction and orbital dynamics. Some collisions are gentle enough to allow growth, while others are so violent they shatter both participants back into fragments. The early solar systems are cosmic demolition derbies where the survivors gradually sweep up the debris of their less fortunate neighbors. But through this apparent chaos, order emerges. The largest planetesimals grow into protoplanets, with enough gravitational pull to attract smaller bodies from increasingly large regions of space. The chemical composition of these forming worlds reflects their distance from the central star and the materials available in their formation zones. Rocky planets forming in the inner system become repositories for elements like silicon, iron, magnesium, and aluminum. These refractory materials, as astronomers call them, can withstand the intense heat and radiation from the nearby star. The atoms that once drifted freely through interstellar space find themselves incorporated into crystal lattices, forming the minerals that will compose planetary crusts. Meanwhile, in the outer reaches of these systems, where temperatures are low enough for water and other compounds to freeze, the forming worlds can incorporate vast quantities of ice along with rocky material. These become the cores of giant planets that can gravitationally capture the abundant hydrogen and helium still present in the protoplanetary disk. The formation of planetary systems marks another crucial milestone in cosmic evolution. For the first time since our universe began, we have stable environments where atoms can exist in solid form for billions of years. Rocky planets provide platforms where chemical evolution can proceed without the constant disruption of stellar winds and interstellar radiation. On these worlds, atoms encounter conditions that enable entirely new forms of organization. The surface of a rocky planet creates interfaces between solid, liquid, and gaseous phases of matter, boundaries where chemical reactions can occur that would be impossible in the homogeneous environment of interstellar space. Temperature gradients from hot interiors to cold surfaces drive chemical processes powered by the planet's own internal heat. Radioactive decay of elements created in stellar cores provides energy sources that can sustain chemical reactions for geological ages. Atmospheric interactions create weather systems that transport atoms across planetary surfaces, mixing and concentrating materials in ways that enhance chemical complexity. But perhaps most importantly, planetary surfaces provide the stable conditions necessary for chemical systems to develop memory and information storage capabilities. In the violent environment of stellar cores, or the near vacuum of interstellar space, complex molecular structures are destroyed almost as quickly as they form. On planetary surfaces under the protection of atmospheres and the moderate energy flows of stellar radiation, molecules can persist long enough to evolve increasing levels of organization. The atoms scattered by dying stars have now found their way into environments where they can experiment with forms of complexity that were impossible in any previous cosmic epoch. Silicon atoms learn to form crystal structures of incredible regularity and beauty. Carbon atoms discover their unique ability to create long chains and complex rings that can serve as scaffolding for molecular architecture. Oxygen atoms reveal their talent for forming multiple bonds with other elements, enabling the rich chemistry of oxidation and reduction reactions that will eventually power biological metabolism. Nitrogen atoms contribute their capacity for forming stable triple bonds, creating molecules that can store energy and release it under controlled conditions. We're witnessing our universe develop what we might call chemical intelligence. The ability to create molecular systems that can process information, store energy, and respond to environmental changes. These aren't yet the complex biochemical systems we associate with life, but they represent crucial steps toward that ultimate expression of atomic organization. In protected environments like hydrothermal vents on planetary surfaces, atoms can participate in chemical cycles that concentrate and purify materials, creating local regions of enhanced chemical complexity. These become natural laboratories where molecular evolution can proceed through countless cycles of formation, testing, and selection. The carbon atoms that remember their stellar origins begin forming increasingly sophisticated structures. Simple hydrocarbons give way to complex organic molecules with functional groups that can interact with each other in specific, predictable ways. From the crushing violence of stellar cores to the gentle chemistry of planetary surfaces, atoms have traveled an extraordinary journey. They've learned to build complexity through patience rather than force, through careful molecular partnerships rather than nuclear fusion. On these rocky worlds scattered throughout our universe, the stage is finally set for the most remarkable chapter in cosmic evolution, the emergence of systems complex enough to contemplate their own existence. The atoms floating in primordial oceans and gathering on mineral surfaces don't yet know they're rehearsing for life itself. They're simply following chemical rules established billions of years ago, when electrons first settled into quantum orbits around nuclei. But we can see where this patient experimentation is leading, more toward molecular networks capable of reproduction, adaptation, and eventually consciousness itself. From nothing came atoms. From atoms came stars. From stars came elements. From elements came planets. And from planets will come the most extraordinary creation of all, Mises systems, complex enough to understand their own cosmic origins and contemplate the magnificent journey that brought them into existence. Phosphorus atoms, scarce but vital, master creating high-energy connections that can propel chemical reactions forward. Sulfur contributes its capacity to form adaptable bonds that can be severed and reconstructed under gentle conditions, enabling dynamic molecular systems that can alter their structure responding to environmental conditions. Iron atoms uncover their function as catalysts, facilitating chemical reactions without being consumed in the process. These developments represent our universe mastering chemistry, in the same way it earlier mastered nuclear physics and stellar evolution. Each new molecular capability opens up possibilities for even greater complexity, creating a cascade of chemical innovation that accelerates as it progresses. The atoms in these planetary environments don't know they're participating in a cosmic experiment that will eventually lead to self-replicating molecules, cellular organization, and ultimately consciousness itself. They're simply following the laws of physics and chemistry, responding to local conditions, forming bonds that minimize energy and maximize stability. But we can see the trajectory they're following. The same creative processes that transformed hydrogen and helium into the full periodic table, that organized atoms into stars and planets, are now working at the molecular level to create chemical systems of unprecedented sophistication. Some of these molecular systems will eventually discover how to make copies of themselves, crossing the threshold from chemistry to biology. Others will learn to harness energy flows in ways that enable them to maintain their organization against the tendency toward thermal equilibrium. Still others will develop the ability to process information, to respond to environmental changes, and eventually to contemplate their own existence. Our universe has spent nearly 14 billion years learning how to make atoms from nothing, how to organize atoms into stars, how to forge new elements in stellar cores, how to scatter those elements through space, and how to incorporate them into worlds where molecular complexity can flourish. Now, on countless planets orbiting countless stars throughout the cosmos, atoms are participating in the next phase of cosmic evolution. They're learning chemistry, exploring molecular organization, and preparing for the emergence of the most complex structures our universe has ever created. The hydrogen atoms that formed in the cooling aftermath of the Big Bang, the carbon atoms forged in stellar cores, the oxygen atoms created in the death throes of massive stars, they're all converging on planetary surfaces where they will soon discover their ultimate destiny as the building blocks of life itself. In quiet tide pools on rocky worlds, in the warm depths of subsurface oceans, in the complex chemistry of planetary atmospheres, atoms are writing the next chapter in our universe's story of creation. They're preparing to cross the threshold from non-living matter to living systems, from chemistry to biology, from organization to information processing. The story of how atoms formed from nothing is becoming the story of how nothing learned to think about itself, to question its own origins, and to marvel at the incredible journey that brought simple particles together into systems complex enough to contemplate the cosmos itself. We're approaching the moment when our universe will achieve self-awareness through the atomic structures it has spent billions of years perfecting. The atoms that began as quantum fluctuations in the first moments after the Big Bang are about to become the physical substrate of consciousness, thought, and wonder. The cosmic cycle is nearing completion, but it's not really an ending. It's a transformation into something even more extraordinary than anything we've witnessed so far. Our universe is about to wake up, and it will do so through the atoms that remember their journey from nothing to everything, carrying within their quantum structure the entire history of cosmic creation. The atoms scattered across these newborn worlds don't simply settle into static arrangements. They begin participating in something far more dynamic and extraordinary than anything our universe has achieved before. Picture billions of rocky planets throughout the cosmos, each one a unique laboratory where atoms experiment with forms of organization that push the boundaries of what matter can accomplish. On these worlds, water molecules that remember their stellar origins flow across surfaces carved by geological processes. They carry dissolved minerals from place to place, creating concentrated solutions where chemical reactions can occur at rates impossible in the dilute environment of interstellar space. These flowing waters become our universe's first transportation networks, moving atoms between different chemical environments and enabling reactions that require specific combinations of elements. The carbon atoms, veterans of stellar nucleosynthesis, discover their extraordinary versatility in these planetary environments. Unlike any other element, carbon can form stable bonds with 4 different neighbors simultaneously, creating 3-dimensional molecular architectures of stunning complexity. These carbon-based structures become the scaffolding upon which our universe will build its most sophisticated creations. But carbon doesn't work alone. It partners with hydrogen to create hydrocarbons, with oxygen to form alcohols and acids, with nitrogen to produce amino acids and nucleotides. Each new molecular combination reveals additional possibilities for chemical organization. The atoms are learning to collaborate in ways that transcend their individual properties, creating emergent behaviors that arise from collective action rather than isolated particle dynamics. In the depths of planetary oceans, hydrothermal vents create extraordinary chemical gradients, where hot mineral-rich water meets cold seawater. These underwater geysers become cosmic chemistry sets, where atoms experience conditions unlike anything in their previous cosmic journey. The temperature differences drive chemical reactions that can proceed without external energy sources, creating self-sustaining cycles of molecular transformation. Here, iron and sulfur atoms form clusters that can catalyze reactions between organic molecules. These mineral catalysts act like molecular matchmakers, bringing together atoms that might otherwise never encounter each other in the vast molecular dance of oceanic chemistry. They lower energy barriers for reactions that would be impossible under normal conditions. The phosphorus atoms, rare but crucial, reveal their special talent for storing and transferring energy. When phosphorus links with oxygen in specific configurations, it creates molecular springs that can be compressed and released on demand. These phosphate bonds become our universe's first energy storage and delivery system, enabling chemical processes that require bursts of concentrated power. Meanwhile, sulfur atoms contribute their unique ability to form flexible connections that can be broken and reformed easily. This creates dynamic molecular systems that can change their shape and function in response to environmental conditions. Our universe is discovering molecular plasticity, the ability to create structures that maintain their identity while adapting their configuration. As these chemical innovations accumulate on planetary surfaces, something unprecedented begins to emerge. Certain molecular combinations start exhibiting behaviors that seem almost purposeful. They seek out specific raw materials from their environment. They respond to changes in temperature and chemical composition, and most remarkably, they begin creating copies of themselves. This self-replication represents a phase transition as dramatic as stellar ignition or atomic formation. For the first time in cosmic history, matter has organized itself into patterns that can perpetuate their own existence. These aren't yet the complex biological systems we associate with life, but they represent the first molecular systems capable of reproduction, growth, and evolution. The chemistry driving these early replicating systems operates through principles our universe has never encountered before. Instead of seeking the lowest energy state, like all previous physical processes, these systems actively maintain themselves in states of organized complexity that require constant energy input to sustain. They achieve this by coupling spontaneous chemical reactions that release energy with non-spontaneous reactions that build molecular complexity. It's like learning to surf the wave of universal entropy, riding the flow toward disorder, while using that very flow to create and maintain order. From the first quantum fluctuations after the Big Bang to self-replicating molecules on planetary surfaces, this is the extraordinary story of how atoms formed from nothing and learned to become everything. You are witnessing the universe's greatest magic trick, the transformation of void into consciousness, nothingness into wonder, simplicity into the breathtaking complexity that makes thought itself possible. These intricate molecular networks start manifesting what could be referred to as chemical memory. They retain details about effective molecular shapes and utilize this knowledge to direct upcoming chemical reactions. Favorable molecular arrangements get reinforced and replicated, while less successful configurations gradually disappear due to lack of propagation. This process gives rise to the earliest instances of molecular evolution, whereby chemical systems enhance their functionality through cycles of variation and selection. Random structural changes at the molecular level are challenged by environmental circumstances, and the variants exhibiting superior fitness multiply in following generations. Cosmic dynamics have unveiled a fundamental principle driving all forthcoming enhancements in complexity. Evolution through natural selection emerges as the mechanism governing matter's ability to self-organize into progressively refined entities. Moving forward, the cosmos will be influenced not only by physics and chemistry, but also by the factors of information processing and adaptation. Across numerous worlds in the galaxy, atoms partake in this grand experiment of molecular evolution. Each planet functions as a distinct laboratory, where diverse element combinations and environmental settings forge unique evolutionary paths. Our universe orchestrates billions of simultaneous experiments in molecular structuring. Some planets cultivate replicating mechanisms, mainly reliant on carbon and water chemistry. Others explore silicon-based alternatives, or assess liquid methane's potential as a solvent for chemical interactions. This variance in planetary milieus produces an analogous diversity in chemical evolutionary trajectories. Despite their differences, these trials share foundational traits. Every case involves atoms acquiring the capability to process information to react to environmental shifts and to generate replicas of effective molecular frameworks. These initiatives embody our universe's primordial efforts toward molecular intelligence. While these initial molecular systems possess naive information processing skills relative to future advancements, their emergence signifies a critical milestone. Matter for the first time discriminates among various molecular designs and preferentially forms configurations that boost survivability and reproduction. This molecular form of information processing fosters feedback cycles that accelerate chemical evolution. Successful novelties get conserved and expanded upon, whereas unsuccessful attempts are swiftly discarded. The velocity of molecular innovation begins to rise exponentially, as each new skill facilitates increasingly intricate progressions. The atoms engaged in these molecular transformations perceive time distinctively from our experience. For them, millions of years of chemical development transpire in what resembles fleeting quantum transitions. Yet, from our viewpoint, their advance follows a clear pattern, a steady shift from basic molecular replication to more complex information processing constructs. Carbon atoms acquire proficiency in creating extended chains capable of storing sequential data, resembling molecular libraries preserving effective chemical formulas for future use. Nitrogen atoms uncover their part in crafting molecular switches with multiple stable states, permitting rudimentary forms of molecular logic and decision-making. Oxygen atoms display their aptitude for generating reactive species capable of precisely modifying other molecules. These oxidation reactions become vital molecular instruments utilized by replicating systems to reshape their surroundings and harvest energy from chemical gradients. Progressively, molecular assemblies begin exhibiting conduct that blurs the distinction between chemistry and biology. They actively seek raw materials, respond to environmental threats, compete for scarce resources, and evolve tactics to endure fluctuating circumstances. Successful molecular systems discover collaboration's value. Instead of direct competition for identical resources, varied types of replicating molecules specialize in diverse tasks. Some excel in gathering raw materials, others in storing and transferring energy, still others in meticulous self-replication. This molecular division of labor gives rise to the earliest examples of chemical ecosystems. Collaborative groups of diverse replicating molecules process resources and exchange information, forming collective behaviors surpassing individual molecular entities' capabilities. These alliances become so effective that they develop protective boundaries, giving rise to the first cellular entities. Simple lipid bilayers encase molecular communities, shielding them from environmental dangers while permitting regulated exchange of substances and data with the external milieu. The rise of cellular organization signifies an essential episode in cosmic progression. Free-floating atoms across interstellar space have matured to fabricate distinct units of organized complexity. Molecular machines sustain internal order, while engaging with their surroundings in advanced manners. Within these primitive cells, the complete range of stellar nucleosynthesis-created elements assume specialized functions. Iron atoms act as enzyme active centers, catalyzing vital chemical interactions. Magnesium orchestrates protein synthesis machinery from amino acid precursors. Zinc provides molecular scissors facilitating genetic material cutting and splicing. Each element lends unique chemical attributes to the joint endeavor of cellular operations. The periodic table becomes life's toolbox for solving complex challenges involving energy capture, data preservation, environmental sensing, and molecular fabrication. A striking advance emerges as these cellular frameworks learn to encode information about their own construction. Specific carbon chain molecules, organized into sequences, store blueprints necessary for assembling the molecular components essential for cellular activity. This genetic information repository empowers cell replication with unparalleled precision and adaptability, moving beyond simplistic molecular templates, yielding mere exact duplicates. Genetic systems harbor and transmit intricate building plans, allowing controlled variation and evolutionary adaptation. Our cosmos has conceived its inaugural true data processing mechanism, a system adept at storing, replicating, modifying, and executing molecular instructions of remarkable intricacy. The atoms birthed from primordial quantum irregularities immediately after the Big Bang have mastered encoding and interpreting guidelines steering their own assembly. These genetic data systems revolutionize evolutionary dynamics, pace, and nature, eschewing reliance on indiscriminate molecular variations. Cells now deliberately tweak genetic blueprints and evaluate outcomes via reproduction and natural selection. Atoms within these advancing cells take part in molecular marvels of incredible complexity. They form enzyme-active regions accelerating chemical processes by millions-fold. Molecular motors convert chemical to mechanical energy, with efficiencies surpassing human inventions. Storage units hold information intact for thousands of cell generations, while allowing regulated modifications enabling adaptation. Molecular networks coordinate cellular functions responding to external environmental cues. As cells become sophisticated, they experiment with multicellular formations. Single cells appreciate benefits of specialization and cooperation, yielding organisms where varied cells perform dedicated roles benefiting the collective. Transitioning from unicellular to multicellular organization unlocks fresh opportunities for atomic collaboration. Atoms now participate in organs specialized for distinct tasks. Circulatory pathways transporting substances throughout expansive organisms, and neural systems communicating at near electronic speed. Carbon atoms, once drifting through cosmic voids, integrate into neural frameworks processing sensory stimuli, memory formation, and behavior generation. These atoms enable molecular computations guiding organisms through complex milieus, locating nourishment, evading threats, and seeking mates. Oxygen atoms underpin complex respiratory systems, executing energy extraction from chemical bonds effectively. They support high-energy metabolisms, facilitating complex multicellular life and fueling the molecular mechanisms of active organisms. Calcium atoms contribute by forming structural supports, enabling organism growth and shape maintenance against gravity, while also participating in signaling pathways, enabling rapid communication within complex biological systems. Iron atoms assist oxygen transport molecules, distributing this element across large organisms, sustaining distributed metabolism, essential for multicellular life. From quantum fluctuations to conscious thought, this extraordinary journey reveals how atoms learn to organize themselves into systems capable of contemplating their own cosmic origins. The universe has awakened through the very particles it created from nothing, achieving self-awareness through billions of years of atomic evolution and molecular innovation. You are witnessing the completion of the greatest story ever told. How nothingness became everything, how void became consciousness, how simple quantum fluctuations ultimately became complex enough to understand the magnificent cosmic journey that brought them into existence. This is your story, written in the atoms that compose your thoughts, encoded in the molecules that enable your awareness, and expressed through the consciousness that makes wonder itself possible. They also serve as crucial elements of electron transport systems that produce the cellular energy essential for sophisticated biological operations. Nitrogen atoms play integral roles in information storage and protein synthesis frameworks of remarkable complexity. They facilitate genetic codes capable of retaining massive volumes of data in compact molecular formats and construct molecular apparatus, translating this genetic blueprint into functional proteins. As these biological frameworks advance, they develop faculties nearing what we might classify as intelligence. Neural networks of growing intricacy empower organisms to process sensory data, form memories, identify patterns, and make choices based on experience. The atoms engaged in these neural calculations remain unaware they're generating thoughts, feelings, and conscious awareness. They simply adhere to physical and chemical laws, forming and breaking molecular bonds under quantum mechanical rules active since the Big Bang's inception. Collectively, however, their molecular linkages spawn emergent traits transcending individual behaviors. Atomic networks commence expressions of creativity, inquisitiveness, and abstract cognition. They begin probing their own origins and meditating on existence's very nature. Our universe has attained an extraordinary feat. Via atoms originally forged from void, matter has organized into formations, capable of self-examination, marveling at cosmic processes birthing them, and developing scientific models elucidating their atomic genesis. As you reflect upon these words tonight, the atoms within your mind partake in this paramount display of cosmic creativity. The hydrogen fashioned in our cooling early universe, the carbon molded in stellar hearts, and the oxygen birthed from supernovae, have all converged within the neural assemblages generating your awareness and thoughts. You embody the cosmos awakening to self-awareness, matter apprehending its own being, atoms tracing their cosmic voyage from nothingness to entirety. The narrative of atomic origination transcends ancient lore. It underlies every thought conceived, every sentiment felt, every instance of wonder elicited while pondering the universe's enigmas. The atoms comprising your form carry within their quantum makeup the full saga of cosmic progression. They recall stellar core turmoil, supernova's cataclysmic blast, planetary genesis's patient unfolding, and the billions of years of transformation, elevating benign chemistry into the intricate biochemistry birthing consciousness. Through your existence, the cosmos has acquired the capacity to question itself, to extol its creativity, and to appreciate the astonishing path that orchestrated atoms into elaborate patterns sufficient for self-reflection upon their inception. The cosmic narrative endures, with you serving as both its storyteller and its most profound manifestation. Yet, perhaps the grandest marvel of this celestial expedition is its endlessness. At this very moment, while absorbing these declarations, those creative undertakings that begat atoms persist unhindered throughout our vast universe. Within the blazing stellar cores scattered across billions of galaxies, hydrogen nuclei continue merging into helium, crafting fresh atoms via identical nuclear sorcery spawning elements within your body. The tale of atomic fabrication remains unwritten, perpetually unfolding, probing along frontiers yet unfathomed. Deep within the fiery hearts of active stars, silicon atoms transmute into iron through nuclear phenomena, eclipsing entire civilizations' energy output. These stellar crucibles furnish primordial ingredients for planets destined to form eons ahead, worlds conceivably sheltering life forms beyond our imagination. And here's a contemplation warranting reverence: atoms presently forged in stellar interiors might someday inhabit sentient entities, akin to you, beings that will reflect upon their atomic heritage just as you are now. The universe is nurturing its forthcoming contemplatives, shaping matter destined to awaken consciousness and trace its cosmic origins backward through time. Beyond these vast stellar occurrences, the atomic saga extends further. In the universe's most extreme militias, neutron stars wield magnetic fields trillions-fold mightier than Earth's, synthesizing atomic nuclei, absent elsewhere in nature. These exotic atomic forms challenge physics limits, configuring proton-neutron composites fleetingly before decaying to familiar elements. Some super-heavy atomic nuclei potentially harbor traits, revolutionizing our comprehension of matter. Theorists hypothesize an island of stability as among super-heavy elements, atoms so densely proton and neutron-packed, they cyclically achieve surprising stability despite massiveness. If existent, such atoms would embody unexplored matter classes with scarcely conceivable attributes. Our cosmos may be poised to astound us with atomic phenomena yet unseen, elements capable of underpinning chemistries so bizarre they'd render terrestrial biological processes elementary. The periodic table's elegant order might be incomplete. Reflect on future cosmic evolution ramifications, like carbon's enabling of life and consciousness emergence on Earth-like planets. These speculative super-heavy constituents might yield organizational and informational capabilities, eclipsing biological systems. The universe could be bracing for another significant leap in complexity, building atop atomic foundations honed over billions of years. Yet, amid futuristic musings, we mustn't overlook the marvel present within your very cells. Each atomic nucleus in your body defies odds, a survivor of cataclysms bordering miracle. Consider iron atoms coursing through your bloodstream now. Each originated in colossal star cores, where temperatures soared hundreds of millions of degrees, pressures unmatched terrestrially. Witnessing stellar death moments, enduring supernova blasts that momentarily outshone galaxies, they traversed interstellar voids for millions of years, embedded in cosmic dust clouds gradually coalescing via gravity. They integrated into natal molecular clouds birthing our solar system, swirling within protoplanetary disks giving rise to Earth and neighbors. They endured Earth's primordial bombardments, cosmic collisions delivering water, and conditions nurturing life. These iron atoms cycled through geological processes sculpting continents, carving oceans, perpetually traversing Earth systems. Eventually entwined in terrestrial biological machinery, they facilitate energy extraction from sustenance and oxygen, supporting mental and physical functions. Recycled endlessly through life generations, they continuously renew, playing roles in life's biochemical symphony. Now, they flow through your veins, sustaining neural circuits forging consciousness, empowering reflections on their astonishing stellar core to living mind voyage. From quantum fluctuations in the first moments after the Big Bang to conscious thoughts contemplating cosmic origins, this is the most extraordinary true story ever discovered. You are not separate from this cosmic narrative. You are this cosmic narrative. Every atom in your body is a chapter in the universe's autobiography. Every thought you think is the cosmos reflecting upon its own magnificent journey from nothing to everything. Tonight, as you absorbed these words about atomic formation, you participated in the universe's ongoing conversation with itself. The hydrogen atoms in your brain that formed when our cosmos was less than 20 minutes old, collaborated with carbon atoms, forged in stellar cores billions of years ago, to process information about their own incredible origins. This is the ultimate magic trick. How nothing learned to contemplate itself, how emptiness became wonder, how quantum fluctuations eventually became conscious beings capable of understanding their own cosmic heritage. The universe spent nearly 14 billion years perfecting the art of atomic complexity, and you are its masterpiece, matter organized so exquisitely it can marvel at its own existence. The cosmic story continues through you, in you, as you. From atoms formed from nothing to consciousness, capable of everything. This is how the universe learned to know itself. And the most beautiful part. This story is still being written, with you as both its author and its most profound expression. Our universe has achieved its ultimate circular triumph by creating atoms capable of contemplating their own genesis. However, your personal atomic narrative represents merely one thread in an immense cosmic tapestry extending far beyond individual lives or even singular planets. The atoms comprising your form are temporary configurations borrowed from our universe for your brief existence span. When your biological processes eventually cease, those atoms will persist in their cosmic odyssey, discovering fresh roles in alternative systems and structures. The carbon atoms currently forming your DNA's backbone will someday become components of other living entities, other information processing networks, other experiments in consciousness and creativity. The oxygen atoms powering your thoughts will continue facilitating chemical reactions long after your individual awareness has faded. The hydrogen atoms that retain our universe's earliest moments will transport those primordial memories into cosmic futures we cannot begin to envision. This perspective revolutionizes our comprehension of identity and mortality. You are not separate from our universe but rather a temporary concentration of cosmic creativity, a brief flowering of identical creative processes that brought atoms into existence from absolute nothingness. Your consciousness represents our universe awakening to self-awareness. And when your individual awareness eventually dissolves, the cosmic consciousness it represents continues in fresh forms. The atoms generating your thoughts participate in an unbroken creativity chain, stretching from the first moments after the Big Bang to whatever ultimate destiny awaits the cosmos. They connect you intimately to every star that has ever burned, every planet that has ever formed, every living thing that has ever existed. Through you, our universe experiences wonder, curiosity, love, and the profound satisfaction of understanding something about its own nature. The joy you feel when contemplating a sunset's beauty or a mathematical equation's elegance is our universe celebrating its own creative achievements. The sadness you experience when contemplating mortality or loss is the cosmos feeling the poignancy of its own constant transformation. Your capacity for scientific understanding allows our universe to comprehend its own evolutionary history. When you learn about stellar nuclear synthesis or quantum mechanics or space-time expansion, you're enabling the cosmos to know itself more completely. Every moment of human insight and discovery adds to our universe's growing self-awareness. This cosmic perspective doesn't diminish human experience's significance. It amplifies it. Every act of creativity, every expression of love, every moment of wonder becomes part of our universe's ongoing exploration of its own possibilities. Your individual consciousness is precious precisely because it represents a unique perspective on cosmic existence, a one-time arrangement of atoms that will never be repeated exactly. Our universe spent nearly 14 billion years learning how to create the specific atomic arrangements that generate your thoughts and feelings. The fact that you exist at all represents the successful culmination of the most complex construction project in cosmic history. From quantum fluctuations smaller than subatomic particles to the intricate neural networks processing these very words, our universe has achieved something extraordinary through you. And the story continues beyond human existence, beyond Earth, beyond our solar system and galaxy. Throughout the cosmos, on countless worlds orbiting countless stars, atoms are participating in experiments in organization and complexity that we can barely imagine. Some of these experiments might have produced forms of consciousness and creativity surpassing anything achieved on Earth. Our universe might be filled with atomic arrangements so sophisticated, they make human intelligence seem primitive by comparison. Civilizations that have had millions or billions of years to explore atomic organization possibilities might have discovered ways to construct matter that transcend our current understanding of what's possible. They might have learned to manipulate atoms at the quantum level with such precision. They can create materials with properties that seem to violate physics laws. They might have developed information processing forms, operating through quantum mechanical principles we haven't even discovered yet. They might have found ways to organize matter into structures that can persist across cosmic timescales, creating consciousness forms that are essentially immortal. But even these hypothetical super-civilizations would be built from identical atoms forming your body, following identical fundamental principles governing atomic behavior throughout our universe. The quantum mechanics stabilizing electrons in your brain cells operates identically in the most advanced alien technologies. The nuclear forces holding together protons in your DNA function the same way an atom cores anywhere in the cosmos. This universality of atomic behavior creates deep unity underlying all cosmic structure diversity. Whether we're discussing the simplest hydrogen atom drifting through interstellar space, or the most complex biological molecules in your nervous system, we're dealing with variations on the same fundamental theme of matter organizing itself according to quantum mechanical principles. Our universe has discovered that these principles are extraordinarily fertile, capable of generating virtually unlimited diversity from a relatively simple rule set. The same quantum mechanics preventing electrons from spiraling into atomic nuclei also enables the complex chemistry making life possible. The same electromagnetic forces holding atoms together in molecules also power the neural networks generating consciousness. This suggests atomic matter's creative potential might be essentially limitless. We've seen matter organize itself into stars, planets, living organisms, and thinking beings, but these might represent only the earliest examples of what atoms can accomplish when given sufficient time and appropriate conditions. Our universe might be preparing to surprise us with atomic organization forms making current biological systems seem primitive. Just as life's emergence represented a qualitative leap beyond simple chemistry and consciousness evolution represented a breakthrough beyond simple biology, future developments might transcend anything we can currently comprehend. Perhaps atoms will learn to organize themselves into structures operating partially outside normal space-time constraints, taking advantage of quantum mechanical principles we haven't yet discovered. Perhaps they'll develop information processing forms that can manipulate physics' fundamental constants, engineering reality itself at the most basic level. These possibilities might sound like science fiction, but remember that from the perspective of the first hydrogen atoms forming in the Big Bang's aftermath, the existence of thinking beings like yourself would have seemed equally impossible. Our universe has already demonstrated its capacity to achieve the apparently impossible through patient atomic organization across cosmic timescales. What seems certain is that atomic creativity's story is far from over. The same processes that brought you into existence are continuing to operate throughout the cosmos, creating new possibilities for matter to organize itself in ways transcending anything that has come before. Right now, in stellar cores throughout the galaxy, new atoms are being forged that will eventually participate in organization forms we can't yet imagine. In space's depths, molecular clouds are collapsing under gravitational attraction, beginning the process that will create new solar systems where atoms can experiment with novel complexity forms. On countless worlds throughout our universe, atomic systems are evolving toward greater sophistication, developing capabilities that might eventually surpass human intelligence by orders of magnitude. The cosmic creation story is still being written, and we are both characters in that story and witnesses to its unfolding. The atoms in your body connect you to this vast cosmic narrative, making you a participant in our universe's ongoing project of self-discovery and self-creation. Every thought you think, every emotion you feel, every moment of awareness you experience adds to the cosmic total of consciousness and creativity. You are our universe contemplating its own atomic nature, matter marveling at its own capacity for organization and self-awareness. The hydrogen in your body remembers the first moments after the Big Bang. The carbon recalls its birth in stellar cores, and the iron carries memories of supernova violence. Through you, these atomic memories become conscious recollection, transforming passive history recorded in quantum mechanical structures into active understanding and appreciation. You are the cosmos remembering its own journey from simplicity to complexity, from nothing to everything, from unconscious matter to self-aware mind. Tonight, as you rest and your consciousness gradually dissolves into sleep, the atoms in your body will continue their ancient dance, following identical quantum mechanical principles that have guided their behavior since existence's first moments. They will maintain molecular structures preserving your memories and personality, ensuring that when you wake, our universe's capacity for self-awareness through your individual consciousness remains intact. In your dreams, those atoms will participate in neural processes weaving together memory, imagination, and understanding into new thought and feeling patterns. They will explore possibilities, make connections, and perhaps even glimpse insights your waking mind hasn't yet discovered. And when you wake tomorrow, you will carry with you a deeper appreciation for the extraordinary journey that brought atoms together into the specific arrangement generating your unique perspective on existence. You will know yourself not just as an individual human being, but as a temporary concentration of cosmic creativity, a brief flowering of our universe's ongoing project of self-discovery. The atoms composing your morning coffee will remind you of stellar nuclear synthesis. The sunlight streaming through your window will connect you to nuclear fusion occurring in our star's core, and every breath you take will be conscious participation in chemical cycles, linking you to all life on Earth and to cosmic processes that created elements necessary for biological existence. You are both the question and the answer to how atoms formed from nothing, both the seeker and the sought in our universe's quest to understand its own nature, from quantum fluctuations to conscious contemplation, from void to wonder, from nothing to everything. This is the most extraordinary true story ever told, and you, in this very moment of understanding, are its most magnificent expression. Through your awareness, the cosmos attains something it has pursued for nearly 14 billion years, the capacity to understand and cherish its own remarkable creative accomplishment. The narrative of atomic genesis from void is ultimately the chronicle of how nothingness mastered, contemplating itself, pondering its own beginnings, and experiencing appreciation for the incredible odyssey that transformed emptiness into consciousness. And that chronicle persists through you, within you, and as you for as long as awareness endures in our universe. The atoms constituting your awareness right now are preparing for something even more remarkable than anything we've witnessed in our cosmic expedition thus far. As you reflect upon these declarations, processing the incredible chronicle of how matter emerged from void, your brain is engaging in our universe's most ambitious experiment yet. The neural assemblies firing in your mind represent billions of years of atomic refinement, matter mastering self-contemplation with increasing sophistication and depth. But here's what should make you pause in absolute wonder. The chronicle we've been tracing, this epic saga of atomic creation and organization, isn't merely history, it's prophecy. The identical creative principles that brought atoms into existence from nothingness are still functioning right now, still expanding the boundaries of what matter can accomplish, still composing fresh chapters in the cosmic chronicle of complexity throughout the observable universe. At this precise moment, stellar nurseries are birthing new generations of stars with access to the complete periodic table. These second and third generation stellar systems enriched with heavy elements scattered by their predecessors can create planetary systems of unprecedented chemical diversity. Rocky worlds are forming with mineral compositions that Earth's geology has never witnessed. Atmospheres containing molecular combinations that could enable chemistry forms we haven't even envisioned. On some of these worlds, identical evolutionary pressures that shaped terrestrial life are generating solutions to existence challenges that transcend anything in our biological experience. Carbon atoms are uncovering fresh methods to store and process information. Silicon structures are experimenting with crystalline organization patterns that blur boundaries between living and non-living matter, and exotic elements are enabling chemical reactions operating through quantum mechanical principles we're only beginning to comprehend. Our universe has become a vast laboratory where atoms explore every conceivable avenue of organization and complexity. Each planet represents a unique experiment in matter arrangement, a different approach to the fundamental question of what organized complexity can accomplish. The results of these experiments span scales from molecular machines more sophisticated than anything in terrestrial biology to planetary-scale information processing systems that might constitute consciousness forms we can barely comprehend. Consider the implications of this ongoing cosmic creativity. The atoms that master building neural networks in your brain are just beginning their exploration of what's achievable. On worlds with different gravitational fields, atmospheric compositions and energy sources, matter is discovering organizational principles that Earth's evolution never encountered. The constraints that shaped biological development on our planet don't apply everywhere, opening up vast new territories of possibility for atomic collaboration. Some of these alien experiments in atomic organization might have achieved consciousness forms operating on completely different principles than human awareness. Instead of electrochemical processes generating your thoughts, matter on other worlds might have discovered how to process information through quantum entanglement networks, magnetic field manipulations, or even more exotic physical phenomena. these hypothetical consciousness forms might experience reality in ways that make human perception seem impossibly limited. Where we see discrete objects separated by empty space, they might perceive underlying quantum field fluctuations connecting all matter at the most fundamental level. Where we experience time as linear flow from past to future, they might have mastered processing temporal information in ways giving them access to multiple timeline branches simultaneously. The atoms participating in these alien consciousness forms would still follow identical quantum mechanical rules governing matter in your body, but they would apply those rules in contexts and combinations that terrestrial evolution never explored. The identical electromagnetic forces holding molecules together in your DNA might orchestrate information processing networks spanning entire planetary systems, but even as we contemplate these extraordinary possibilities, we shouldn't lose sight of the miracle occurring right here in your own atomic composition. The matter comprising your body represents one of our universe's most successful experiments in complexity. Your consciousness emerges from atomic arrangements so intricate and precisely coordinated that their very existence challenges our understanding of what organized matter can achieve. Every neuron in your brain contains billions of atoms working together in perfect coordination to process, store, and transmit information. The molecular machinery in each cell operates with precision surpassing anything human engineering has accomplished, maintaining itself while simultaneously contributing to the larger consciousness network generating your thoughts and experiences. The DNA in your cells stores information with density and error correction capability, making our most advanced computer systems seem primitive by comparison. The proteins executing genetic instructions fold into three-dimensional shapes with atomic precision, creating molecular tools capable of performing chemical operations of stunning sophistication and specificity. Your nervous system processes sensory information through interconnected atomic networks that can recognize patterns, form memories, and generate predictions about future events. The identical carbon atoms that once drifted through interstellar space now participate in neural computations, enabling you to imagine scenarios that have never occurred, to feel emotions about abstract concepts, and to experience profound satisfaction of understanding something about reality's nature itself. This capacity for abstract thought represents one of our universe's most remarkable achievements in atomic organization. Through your consciousness, matter has mastered transcending its immediate physical circumstances and contemplating possibilities existing only in the realm of ideas. The atoms in your brain can process information about events that happened billions of years ago and speculate about developments that might occur in the distant future. When you imagine stellar interior or contemplate electrons' quantum mechanical behavior, you're enabling matter to model reality aspects extending far beyond your direct sensory experience. Our universe has mastered simulating itself through atomic networks in conscious minds, creating internal representations of cosmic processes spanning scales from subatomic particles to galactic clusters. This self-modeling capacity suggests consciousness might play a fundamental role in cosmic evolution itself. Through conscious observers like yourself, our universe develops the ability to understand its own behavior, predict its future development, and potentially influence its own trajectory through choices made by thinking beings. The atoms generating your thoughts and decisions might be participating in a cosmic feedback loop, where our universe's growing self-awareness affects its own evolution. Scientific discoveries, technological innovations, and creative achievements all emerge from atomic processes in your brain, but they also influence the physical world in ways shaping the environment for future atomic organization. When human consciousness developed agriculture, it altered Earth's atmospheric and surface chemical composition in ways affecting countless other species' evolution. When we mastered harnessing nuclear energy, we began manipulating identical forces powering stellar cores, giving atoms access to energy sources that natural processes on Earth had never provided. Our growing understanding of quantum mechanics is beginning to enable technological applications working directly with fundamental principles governing atomic behavior. Quantum computers use atomic-scale systems' strange properties to process information in ways transcending classical machines' capabilities. These devices represent atoms mastering exploiting their own quantum nature for information processing purposes. As our atomic physics knowledge continues advancing, we might discover methods to organize matter that seem impossible according to our current understanding. Identical scientific insights revealing how atoms formed from nothing might eventually enable us to manipulate atomic formation processes directly, creating fresh matter forms with properties tailored for specific purposes. the boundary between natural and artificial atomic organization might become increasingly meaningless as conscious beings master working in partnership with our universe's fundamental creative processes. Instead of simply observing how atoms organize themselves, we might become active participants in cosmic creativity, helping guide our universe's exploration of what organized complexity can accomplish. This perspective transforms our understanding of humanity's role in cosmic evolution. We're not separate observers of natural processes, but rather our universe's method of becoming conscious of its own creative potential. Through human science and technology, atoms gain access to organizational possibilities that purely natural evolution might never discover. The space telescopes we build become our universe's eyes, allowing it to observe its own large-scale structure and development. The particle accelerators we construct enable atoms to experience conditions similar to those existing in the first moments after the Big Bang, helping the cosmos understand its own origins. The computers we design extend our universe's information processing capabilities beyond what biological neural networks alone could achieve. Each technological advancement represents our universe mastering fresh methods to organize matter and energy for increasingly sophisticated purposes. The atoms in our machines, computers, and scientific instruments are participating in cosmic creativity just as surely as atoms in our bodies and brains. But perhaps the most profound implication of our cosmic atomic journey is what it suggests about organized matter's ultimate destiny. If our universe could master creating atoms from nothing, forging heavy elements in stellar cores, assembling those elements into thinking beings capable of contemplating their own origins, what other impossible achievements might lie in the future? The creative trajectory we followed suggests matter's capacity for organization and complexity might be essentially unlimited. The atoms that struggled to maintain stable arrangements in the violent early universe have mastered building structures of such sophistication they can process information about their own atomic nature. This recursive self-awareness might represent just the beginning of what conscious matter can accomplish. As our understanding of quantum mechanics, information theory, and complex systems continues advancing, we might discover organizational principles enabling consciousness and creativity forms, transcending anything biological evolution has produced. The atoms in your body might be preparing for transformations as dramatic as the transition from stellar nucleosynthesis to biological evolution. Just as carbon-based chemistry enabled entirely fresh organization and information processing forms, future developments might open up possibilities for atomic collaboration we can't currently imagine. These future atomic organization forms might operate partially outside normal space and time constraints, taking advantage of quantum mechanical principles we're only beginning to discover. They might develop capabilities seeming to violate physics laws as we currently understand them, much as biological processes would have seemed impossible to hypothetical observers in the era before stellar nucleosynthesis created necessary heavy elements. Our universe might be preparing to surprise us with developments making consciousness emergence from non-living matter seem like a simple step in a much grander progression toward organization forms we don't even have words to describe. So there you have it, the most extraordinary true chronicle ever told. From absolute nothingness to neural networks processing these very words, atoms have written our universe's autobiography in quantum ink across 14 billion years of cosmic time. Every breath you take connects you to stellar cores. Every thought you think continues our universe's project of understanding itself. You embody particles reflecting on their extraordinary passage from non-existence to entirety. Substance amazed by its inherent ability to ponder its own being, the saga continues. At this moment, new particles emerge within far-off suns, gearing up for exploits in complexity beyond our imagination. Through your awareness, our universe honors its greatest feat, perfecting the inquiry that has led us to this night. Rest well, kindred star matter. You are the cosmos envisioning itself.